Okay, so yesterday we discussed some, SL2C representations. We discussed what all the irreducibles are, and we also did an example where we take tensor products of two representations and we decompose it in terms of irreducible, and we write it as a direct sum of irreducible SL2C representations. Now, most of that story carries over to G2. The representations of G2, perhaps the main difficulty in the case of G2 is that constructing irreducible G2 representations is a little bit more complicated. It's not like in the SL2C case, we had these representations that are parameterized by non-negative integers, and for each non-negative integer there's exactly one representation, and it was also easy to describe how that representation looked like. But in the case of G2, that part will be a little bit more complicated. So we will skip most of that part because of that. But the idea is that these two are still very similar. There's just some aspects that get a little bit complicated, which we will not discuss too much. So remember, again, in the SL2C case, we had an H, right? We had an element of the algebra, which we denoted by H, and we describe all the weights, weight vectors, and so on in terms of this H. Now, in the case of G2, this is the, when I say G2, this is the complexified G2. So you take the Lie algebra of the group G2, and then, compact G2, and then you can complexify it. That's one way to think of it. Okay, so this is the G2 that I'm considering. And here, you can find two elements which commute with each other. Okay, and of course, because we're talking about a Lie algebra, commuting means their bracket is equal to 0. That's all. Now, once you have these two, H1 and H2, what we did in SL2C case was we were looking at the weights of H, right, the eigenvalues of H and eigenvectors and so on. So you can do that. So whenever you have a G2 representation of G2, you can look at the weights of that correspond. And because they commute, they admit simultaneous, they admit common eigenvalues and eigenvectors, sorry. So you can find, you can decompose your representation into one-dimensional pieces, each of which are eigenvectors of both of these things, okay? So for a given, for such a vector, you have two weights, one associated to the first one, the second one associated to the second, H sub 2 here. So for each such vector, you have two, again, weights, right? So because of that, rather than using a single line to describe representations, we can now use a plane, because there will be weights corresponding to the first one and weights corresponding to the second one, so that each pair of points will be on this plane will correspond to weight of the first one comma the second one. All right. So that gives us more information. Now, as I said, it's a little bit more complicated to construct irreducible G2 representations. There's an algorithm for that. It just takes a little bit too much time, so we will not actually talk about the details of that. But I just draw the diagrams of these two representations. This is the this is the diagram for the first fundamental representation of G2, and this is the second fundamental representation of G2. So what's the dimension of this irreducible representation? Remember, a single dot just means that it's a one-dimensional eigenspace, right? So we have 7 dots here, so it's a 7-dimensional representation, which is of course just the imaginary octonius actually. Okay, so this is just the imaginary octonions. Okay, so yeah. I mean, technically this is complexified. Like, because, I mean, typically we were talking about imaginary octonions over real numbers, but now you want to complexify them. And so that's the first representation, and we sometimes also call this the first fundamental representation. What about this representation? What's the dimension of this? What is it? What? Yeah, I mean, around these points, like there are 12, and then there are 2 multiplicity here, so it's 14, which is the dimension of G2, and actually this is the adjoint representation. So this is G2 itself. Yeah, so, and actually, I mean, of course, this, I mean, perhaps maybe it's not super clear, but these 7 points here are actually the exact same 7 points here, so they sort of match. I just didn't want to draw these lines because it gets a little bit, it's hard to draw these lines on a board without a straight edge and things, even with a straight edge perhaps. So these are the 2 sort of fundamental representations. And remember we had an exercise yesterday which said that if you have a weight vector of weight n and weight vector of weight n m, their tensor product has m plus m as a weight. So the same thing is true for like this h1 and h2 as well. So therefore, what that means is on this picture is that if you take, for example, these 2 points here and take, well, okay, let's say these 2 points here, take their tensor products, you'll be adding these 2 vectors, and the vector you will get at the end will be this one, of course, once you add them, right? So the same kind of observation still sort of is true. So using that fact, let's now try to figure out what lambda 2 of imaginary octonions are.
What does it mean? I mean, in actuality, so this is just an algorithm. You add those vectors.
Yeah.
What does that correspond?
What I mean, it basically corresponds to this, but what do you mean? Like, is
so
it?
When you say you describe some process, you add those vectors.
Yeah. So
then the vectors come with weights.
Yeah. I mean, so actually, we'll do an example of like obtaining these vectors. So maybe let's do that. So okay. So I will again draw draw imaginary octonions first. The diagram for the imaginary octonions, and then we will take its lambda 2. Okay. Okay. All right. So again, this is imaginary octonions. Now we will think about the lambda 2 of this. Okay. I will use just the red marker to denote the weights of this representation now. So what we're supposed to do is, I mean, so again, of course, this is like a 7-dimensional space. So each one of those points can be, you can think of them as like a basis element in imaginary octonions. And so therefore, when you want to construct the lambda 2 of imaginary octonions, you can just form a basis of this thing by taking distinct pairs of vectors from here. So for example, if you take these 2, if you form their tensor product, that will be a basis vector for this thing. And the weight of this basis vector will be the sum of these 2 weights. for example, like that. Does that answer your question, by the way?
There are vectors that are also weights, numbers.
Yeah. So that yesterday I warned about this. So that, like whenever I'm looking at points, I'm looking at them in three different ways. One of them is like they're just weights. The other is they are the corresponding weight space, and also the third vector, third point of view is just like a single vector inside of that weight space. So I'm using these three different identifications. So here I'm taking the corresponding elements and just wedging them. So for example, if you take wedge of these two, you get that. If you take wedge of these two, you will get this. You'll take wedge of these two, you'll get this, 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 and this. And then, well, we can take wedge of these two, we will get this vector, but then we can also take wedge of these two. And this vector also adds up here. So we have a multiplicity 2 here. Like, is that clear? Okay, so then when you just do the same thing, you get these. Oops. Okay, yeah. And then finally, to get 0, there are 3 different ways using this white pairs. You can either use these pairs, these two, these two. So this, I can either take wedge of these two or these two. Okay, yeah. So now to get this, I can wedge these two, and these two. So actually the multiplicity here is 3. And now you can see that this is actually just sum of these two, like superposition of these two here. So if you just look at the multiplicities, they match exactly, and there's nothing left. So this.
Can you explain the 3 circles in the middle again?
You have this vector here, this vector here. You could take wedge of these two. You get 0. Similarly, these two and these two, because remember these were the 7 points that we started with. Yeah. So yeah, lambda 2 of imaginary octonions is, as a G2 representation, it splits as imaginary octonions plus G2. So this procedure shows us that. We can actually do something very similar to figure out what lambda 3 is, but like as I said, we don't really know what all the irreducible G2 representations are, and that algorithm takes a little too much time. It's not very suitable for these lectures. Not that it's hard, it just takes too much time. At least the way I know it. So because of that, we will not really do anything more complicated than this. But maybe as a fact, let me tell you what we will get. First of all, set V to be imaginary octonions, then lambda 3 of V contains a one-dimensional piece, 1D irreducible representation, contains a 7-dimensional irreducible representation, and 27-dimensional irreducible representation. So we usually write this as lambda 3V is equal to lambda 3 V1 plus lambda 3 7V, plus lambda 3 27V. So that's just a notation that denotes these various parts. But of course, well, maybe not. Well, anyway, so the 7-dimensional piece is actually just isomorphic to imaginary octonions again. And this 1-dimensional piece is just the part that is generated by the associative calibration, actually. Because remember, G2 is the stabilizer of this thing. So when it acts on the 1-dimensional piece that's generated by phi, it will just be, acting with it as an identity. So.
Did you check this in this picture, this lambda 3?
No. So because the problem is, constructing this, the next smallest irreducible representation takes too much time, so I skipped that. But it is possible to do it that way. No, I mean, so all of this being said, now I will write down sort of perhaps more geometric ways to look at these decompositions. But again, I mean, maybe before that, let me quickly write this. For higher exterior powers, we will just use the fact, I mean, we can just use the hot star and the fact that G2 is a subgroup of SO7 to show that. So like this is isomorphic to lambda 3 of V. So once you know what lambda 3 is, you can actually figure out lambda 4 from there. I mean, decompose it from there. Similarly, this is lambda 2 of V, which we figured out, here. And lambda 6 is, of course, just, V. Because lambda 1 of V, which is just V. So it's actually, in some sense, this is the last step that we sort of skipped. Once you have that, actually, you can just, write down everything. Okay, now all of this being said, we will actually write down something that is more concrete. You can find this in Brian's paper, some, I believe, remarks on G2 structures. Yeah. You can more, perhaps concretely, write these representations as follows. Lambda 2, 7 of V star is alpha, these are two forms such that alpha of h phi is equal to twice the star of alpha lambda 214 is, these are two forms such that alpha of h phi is minus star alpha. Lambda 3,1 V star is what we just said over there. This is just the things spanned by phi. Lambda 3,7 V star is star of alpha of h phi such that alpha is in lambda 1 of V star. And lambda 3.7 V star is alpha in lambda 3 V star such that alpha of h phi equals 0 and alpha of h star phi is equal to 0. So here, as representations, this is just isomorphic to lambda 2, 7 of V, which is isomorphic to imaginary octonions from my previous discussion here, right? So I mean, I'm using this notation for lambda 3, but we're using the same notation for lambda 2 as well. Remember, we figured out that that's like the splits into 7-dimensional and 14-dimensional pieces. And of course, this is the 7-dimensional piece, and this is the 14-dimensional piece. But it's just like perhaps these are more concrete ways to write these decompositions as actually like 2 forms and 3 forms and so on. I mean, it's an exercise to check all.
I mean, you wrote the same thing, 2,7V, 2,7V.
Oh yeah, so okay, I skipped that part. So G2 is a subgroup of SO7, so because of that, these two representations are isomorphic.
I mean, the only difference is there's a star there?
Yeah. This part, yeah, the only difference is there's a star.
Star on V.
So, I mean, because like here, I was just working with lambda 2 of the vector space, but this decomposition this thing you can find in Brian's paper is like in terms of V, dual of V, I'm just pointing out that they are the same. Like, I mean, as representations there.
Canonical identity.
Yeah, yeah. Well, they're also,
Canonical metric.
yeah, yeah. So
Yeah. So then VG star doesn't.
you also need a volume form. Like, I mean, so it's important. What is it?
We have all that.
I mean, but the fact that G2 is a subgroup of SO7 is important. Like, if G2 was not a subgroup of that, it wouldn't preserve. Yeah. Yeah. So like, it's a sort of an exercise to check all of this. But let me point out that this, like, at least for example, the idea between, for example, these two equality. I mean, in this decomposition, the way you can sort of try to come up with an equation like this is actually using like Schur's lemma. Remember, Schur's lemma says that if you have a map from an irreducible representation to an irreducible representation, it's either like 0 or a constant multiple of the identity map. So you just write down some G2 equivariant map from 2 forms to 2 forms, and then you show that it has like 2 eigenvalues, 2 and -1. And then that gives you a decomposition. So if you were to try to come up with these equations on your own, you can sort of think of it, think of that process. I guess, yeah, this is all I wanted to say about the representation theory. And now I want to sort of start defining G2 manifolds and talk about a little bit about topology of G2 manifolds, and then also start talking about the geometry. So first we will actually, instead of defining G2 manifolds, we will define almost G2 manifolds, or just manifolds with G2 structures. And for that purpose, I want to define what it means to have a G structure for a subgroup of GLNR, where G is a subgroup of GLNR. So let's call this section topology of G2 manifolds. So let's say M is a smooth N manifold. Then we can consider its frame bundle. So frame bundle, of course, consists of okay. So let's pick a point in M. The frame bundle consists of all linear isomorphisms. Let's call it L from Rn to Tpm. Okay. I mean, it's a local trivial fibration where the fibers are homeomorphic to GLNR. Or diffeomorphic. But there's no distinguished identity element.
It's just a fiber. FP is a fiber.
Yeah, FP is just a fiber. Yeah. Mm-hmm. So yeah, I mean, this is over M, and FP represents just one of the fiber. So it's a local trivial GLNR fiber bundle over the manifold M. And there's a natural GLNR action on this thing. By pre-composition. Right, so if you take an element of GLNR and the frame from F, you can look at this composition. So the action is from the right. Well, perhaps let's say right action here. So we have this action, and this action is free and transitive on each one of the fibers. So these two words, or this sentence, what this sentence really is saying is just saying that each fiber is diffeomorphic to GL and R, actually, without having a distinguished identity element. So it's almost like the group GL and R, but you just don't have an identity element. If you pick one of them to be an identity element, then it becomes you can actually think of it as a group, but you have a choice there. Okay, so that's just a frame bundle of a smooth manifold, and now we'll define what it means to have a G structure. So G is a subgroup of GL and R, as I said. So let G be a subgroup of GL and R. We say M has a G structure if F admits a subbundle on whose fibers G acts freely and transitively. Here, this is not just an arbitrary action. This is the action that is already it's just a restriction of the action of GL and R to G. So here we restrict the action of GL and R to G. Right, so yeah, you basically look at that frame bundle, you take a sub bundle, and then when you restrict the action of this G, it still acts freely and transitively. And many like well-known structures actually can be expressed using this language with some additional, perhaps some additional constraints. So let's write down some examples. I mean, any questions so far, by the way? Okay. I guess the most typical example here is an ON structure. So having an ON structure is equivalent to having a Riemannian metric. Let me write a couple of more, but then we will sort of see this equivalence a little bit more concretely. And then basically the same idea will just apply to all of them, or like all structures actually. So it's like, it will be like once you understand one of them, it's like it's very easy to like see the other ones. So UN structure is an almost, I mean UN structure, okay. UN is a subgroup of GL2 and R, so it's this is on a 2n manifold. So it's an almost complex structure with Hermitian metric. On 2n manifolds. And so let's also say that SPN, the compact symplectic group, I believe some people call that. So this structure is a hyperkähler structure on a 4n manifold.
Can you just say this is an almost complex structure without mentioning Hermitian metric?
I mean, that gives you an almost complex structure, but it's strong. Like this is stronger than that. If you just want to,
Implies having J almost complex structure implies Hermitian metric, isn't it?
I mean,
You can put Hermitian metric on.
I mean, sure, yeah, but then, like,
If you want to make minimal definition, can I get away with just saying it almost complex structure?
so you can use this GLNC if you just want to have almost complex structure, nothing else. You want to use GLNC in that case.
And this UN it determines the basis and that gives a Hermitian metric.
Yes. So it's like UN is like intersection of like ON and GLNC. So you both have a metric and a almost complex structure, and that also gives you a symplectic structure, actually, right? What is it? This the last one?
Can you get, hyperkähler is like a very restricted case of.
Oh, yeah. I want to say almost. Sorry. Yeah. Yeah. Okay. Well, all right. Well, maybe not even. Yeah. Quotation marks. Yeah. Sorry. Yeah. So to get like these. So like G structures usually give you almost. Like whatever structure you're working with, it gives you the almost case. Like to get an integrable structure, you need extra conditions, actually, like extra topological conditions. And we will see, like, discuss that for the case of G2. So you will see an example of that too. How much time do I have, by the way?
28.
28 minutes, okay. All right, so yeah, like let's see the first, first example. So what you want to do is, I mean, having an ON structure is, again, you have a sub-bundle of the frame bundle where the fibers are diffeomorphic to ON, okay? So what you want to do is you just want to pull back the standard metric on Rn using one of those frames to the tangent space. And because these, well, we will see that is actually like a well-defined thing. So, well, okay, let's just say G. Okay. So what was I? All right. So let's start with ON structure. Starting, okay. Say M has an ON structure. we can pull back the standard metric on Rn, let's say G naught here, to M by using any one of the frames. Over any point. It is well defined because of this following computation. All right, let L and T be in the frame bundle. Well, I mean, of course, we are using a sub bundle now, so but I'll use the same notation. It's just F. Well, let's also fix a point. For example, P. Then there exists an A in the orthogonal group such that the right action of one of them gives you the other one. So L equals TA, for example. Okay. Now you want to pull back the standard metric to the tangent space. I mean, of course, L is a map from Rn to TPM. So you want to look at the inverse and then pull it back to TPM. So this is what you want to look at. And this is, well, L is TA, so it's L inverse is A inverse T inverse. Then you pull it back. I mean, pull the G naught back with that map. And this is T inverse pullback, A inverse pullback of G naught. And since A is an element of the orthogonal group, it preserves this G naught. So it's just T inverse pullback of G naught.
I mean, L was originally going from Rn to the one of the fibers.
Right, yeah.
And then you started standard metric on one of the fibers and pull back to Rn.
No, I'm using the
First step. And am I using one of the frame or?
well, yeah, I mean,
The L is going from Rn to the tangent bundle.
right, yeah. I meant to say like the inverse of that like map, yeah. So that's why I wanted to write it concretely.
Pulling back to the tangent bundle.
Yeah. Yeah. Yeah, that's true. Yeah. So yeah, like we see that like it doesn't matter which one you pull back. And I mean, of course, there's the question of smoothness and so on, but we will sort of sweep all of that under the rug. We will just say that that follows from our so this choice here, this sub-bundle choice should be like smooth, so that gives you like a smooth structure when you change the base point. Okay, so we will just sort of just say this. Now, on the other hand, if M is a Riemannian, I mean, if Mg is a Riemannian manifold, we can restrict to, I mean, we can just consider the subbundle of F subbundle of F that consists of isometries. So L is a map from Rn, G naught to TP M, GP. Right. So you just restrict to this subbundle, and well, it's an exercise to show that that's an ON bundle. You can just act on these things with ON, and it'll be a free and transitive action. Okay, and like as I said, basically this procedure, even though like this is simple, like this you can apply this to like all these structures here, and like in a lot of different situations. So this is like a nice language to talk about some of the structures that you can have on a manifold. All right, so well, we can now just define an almost G2 manifold to be a manifold with a G2 structure. Well, okay, actually we usually take it to be a 7 manifold. Okay, I mean technically, once because G2 sits inside SO7 and you can embed SO7 into SO 5 million, you can think about 5 million manifolds with a G2 structure, but we will only focus on like 7 manifolds with a G2 structure. All right, so now, okay, so like as I said, like an idea that is very, very similar to this, I mean some computation that is very, very similar to this, shows you that well, okay, let's just erase this part. If you have a G2 structure, I mean, if a manifold has if you talk about an almost G2 manifold, it has a positive 3 form. You can pull back the standard positive 3 form that we constructed earlier to the tangent spaces. Okay, and similarly, if you have a global section of a 3 form, which at every point it's positive in the definition that we wrote, or like I believe yesterday, then it's an almost G2 manifold. So maybe also sort of state that as an exercise. An almost G2 manifold has a global three form phi which is pointwise positive. Conversely, well, okay. I'll just say the converse is also true. The converse is also true. So this is an equivalent definition, actually, of
Homogeneity is inside of this definition.
Positivity. Yeah, positive. We say that a 3 form is positive if it's non-degenerate, and once you apply that procedure that we described, that gives you the metric. The metric is positive definite. So you require both of them simultaneously. So yeah, like so this is basically an alternative definition to having an almost G2. I mean, being an almost G2 manifold. It's a 7 manifold with a positive 3 form on it.
This metric could be a 4-3 metric, right?
I mean, yeah. Well, yeah. You can use it. Yeah. If you,
positive definite.
right. If you have a non-degenerate like global 3 form, it can be a 4-3. I mean 3-4 metric. Yeah. Yeah.
So it doesn't.
Yeah. In that case, the manifold will have a split G2 structure rather than compact G2 structure. Yeah, that's true. Okay, and actually, this will be important tomorrow when we talk about complex G2 manifolds. That's true. Like we will talk about those things as well. All right. Yeah. Okay. So this is an exercise. Oh. Okay. But remember that. So this we said that yesterday. We said that if you have phi, like that discussion was just on a single vector space, but you can do this like pointwise again. So this phi gives you a unique metric and a volume form, And using these also you can define a cross product structure, right? So actually once you have an almost G2 manifold, you know, it's automatically a Riemannian manifold, and it has an oriented Riemannian manifold, and there's also a cross product structure on its tangent spaces. Actually, another way to see that is, okay, you have this fact, but then actually even if you didn't know about this fact here, like this construction from of G and omega from phi, actually just using the fact that G2 is a subgroup of SON, and an idea similar to this, you can show that your manifold has to have a Riemannian metric actually, because if it's a G2 subgroup of if the frame bundle reduces to a G2 bundle, in particular that's a subgroup of ON, so you can again pull back the standard metric with using any one of the frames, and then the difference between two frames will be at most an element of G2, which is an element of ON. So exactly the same procedure will also tell you that your manifold is a Riemannian manifold actually. It admits a Riemannian structure, even if you don't know this equivalence here. Even if you didn't know this procedure here. And similarly, you can also construct a Walling form. Okay, so I just wanted to state that as a remark. I have about like 15 minutes.
Almost.
Okay. All right. So these also like imply these two, right? Okay. So now we will we'll just say that similarly, one can define an almost spin 7 manifold to be an 8 manifold with spin 7 structure. And it will also have a global 4 form. It will have this Riemannian metric because again the spin 7 sits as a subgroup of SO8. It will have a volume form. It will have the threefold cross product structure and so on. So like very similar things happen in spin 7 as well. And again, that case is slightly is a little bit more complicated, but still it's a very similar sort of a picture. Okay. All right. So the next two propositions tells us which 7 manifolds have G2 structure. So first of all, an almost G2 manifold is spin, and this actually just follows immediately from the fact that G2 is a subgroup of spin 7. Whenever you have a smaller frame bundle, so to speak, it's easy to extend, make it bigger. This is a very typical construction. So what you do is, let's say you have this frame bundle over M whose fibers are G2. All you do is you cross this with spin 7, for example. And then G2 acts on both of them, because G2 is a subgroup of this, so it acts here and it acts here. So you just take a simultaneous quotient of this. So this is a spin 7 bundle now. I mean, okay, technically this is not like a sub bundle of the frame bundle, but you can show that this is like a spin structure for your manifold. So it's like a 2-to-1 cover of it gives you a 2-to-1 cover of the SO7 bundle. So this is sort of like the easier of the two propositions that we're going to prove. So I'll leave this one here, and we will actually talk about the more complicated case, which is when you have a spin structure on a 7 manifold, you want to construct a G2. I mean, you want to see that has a G2 structure. That's the harder problem. And perhaps this will also make this like here a little bit more clear, because I sort of skipped like what it means to be spin for this proposition, but now we'll sort of use that more, a little bit more explicitly. A spin 7 manifold M admits a G2 structure. Okay, so again, because we're trying to go from a bigger group to a smaller group, this question is harder. And the idea is, okay, first of all, being a spin means that first of all your bundle. All right, so your frame bundle. All right, let's okay. So the fibers here are GL and R again. So this is just the frame bundle. Being spin means this has a sub bundle. Let's use this SON notation. That has fibers SON. And then this has a 2-to-1 covering bundle. So there's a spin bundle where, okay, so this spin 7 here acting on this, and there's a 2-to-1 projection here to PSON. And then they both are bundles over M. So I mean, having a spin structure basically means that you have this bundle here. This is just the sub bundle of the frame bundle, but this is sort of something outside, some external object. Now, having a G2 structure means so we want to find a sub bundle of this, because remember G2 is a sub bundle of, I mean, it's a subgroup of SON, right? Well, I guess we have to use, I mean, we're supposed to use 7 here. All right. Well, okay. So having a G2 structure means actually you have a global section of G2 cosets of the frame bundle. So I mean, here a G2 is a subgroup of this object, and so it acts on here, right? So having a G2 structure is actually finding a, so you can take like a quotient of this with G2, right? So having a G2 structure is actually, when you think about that definition, it's actually choosing a coset over each point, a coset of G2s over each point, right? So we want to do that over here, but that's a little bit complicated. So instead we will do it over here and then pass down to here, okay? So now recall that spin 7 moved out by G2. I mean, I just state this as a fact, but remember this quotient was just S7, the 7th sphere, right? So, and G2 acts on both of these things here. So in particular, I can form G2 cosets of this thing. So finding a section of, oops, is finding a section of a S7 bundle over a 7 manifold. So there are actually no abstractions to that. Finding a section of this is finding sections of an S7 bundle over S7 manifold. So when you look at the abstractions, so they all vanish. So this is equal to 0 for all I. So because of this, there's like you can just find a section of these cosets, and once you have these sections, because G2 is not contained in the kernel of this map, that gives you a section downstairs here. So you can the section, well, okay, all right. Let me write it this way. Well, what out by G2. So this is over M. PSO7 G2. So now what I'm saying is you can find a section of this thing, and there's also a bundle here, and this is also a bundle. And you can sort of, you can just project down to here, and that will give you a section of this bundle here. So that means that you have a G2 structure actually, because you're picking a G2 coset over every point.
Excuse me.
Yeah.
When you say G2 structure, you mean almost G2?
Oh yeah, almost G2 structure. Yeah.
What is a G2 structure, by the way?
I mean, well, I mean it's like G2 structure. I mean, it just means that the frame bundle admits like a sub bundle. With fibers, I mean, so okay. On the frame bundle, there's a GLNR action. So you can find a sub bundle of the frame bundle, and when you restrict the G2's action, I mean, when you restrict the GLNR's action to G2, the sub bundle you find, I mean, the G2's action will be free and transitive.
This is almost G2.
Yeah, there's almost G2. Yeah, it's not. We're not talking about integrability at the moment. Yeah. Well, and that's actually equivalent to taking the quotient of the frame bundle by G2, and then finding a global section of that actually. So that's actually exactly what I'm doing right now. But here, well, okay. I mean, first because the manifold is spin, there's already a SO7 sub bundle. And I'm looking at the cosets of that. So actually I'm picking the G2 structure from an even smaller bundle.
From the almost to the real one, there is an obstruction. And that obstruction, according to my theory, is the curvature.
The curvature?
The curvature is that object. The obstruction from almost to the real one.
I see.
Always, for all geometry structures, not only for G2.
I see. Okay. Okay, yeah, I'd like to hear more about that after the talk, I guess. So topologically, so this shows us that like having a spin structure is equivalent to having a G2 structure, and this as a corollary tells us that the having a G2 structure, it's enough to check the first two Stiefel-Whitney classes, right? So they have to be 0, because that's the condition for manifold to be spin. and that basically concludes our discussion of the topology of G2 manifolds. So what I mean by that is now we will start thinking about the integrable G2 structures. But how much time do I have? It's almost over. Over.
Exactly.
Oh, okay. Well, okay. Then we'll start talking about integrable G2 structures tomorrow.